Hello everyone, my name is Hamid Arian, and unfortunately because of the viral infection that I have, I didn't have the pleasure to be with you. Today I want to talk about a paper that we have recently published. The title of the paper is Encoded Value at Risk. It's a predictive machine for measuring risk for investment portfolios. What I'm going to talk about in this presentation is how generative neural networks, specifically in this talk, variational autoencoders, can be used to make simulations much easier and much faster, considering the fact that the distribution of the return usually is not something that can be easily simulated. But just like any other talk using AI in investment risk, let me motivate you first. We're going to talk about a variational autoencoder that can be used to generate many scenarios, which are probable to happen but hasn't happened before. This is very similar to many situations in image processing, and interestingly enough, variational autoencoders, they have been used for generating images which are probable, but they haven't really happened in the past, or maybe they've happened, but we don't know if they have. Of course, this is going to provide a lot of benefits for us, but something that is really important, and the legendary quant, Marcos Lopez de Prado, has pointed out in his book, is that usually the ratio of signal to noise is very low. And normally what we do, many of the methods from econometrics that is used in finance usually make it worse, including differentiation, for example. One good news is that this generative machine can indeed increase the signal to noise ratio. We're going to see how. But before we dive into the financial application of this AI machine, let me tell you a bit about what VAEs, or variational autoencoders, do in MNIST modeling, for example. VAEs have a number of latent variables, and it can be seen, it's a stylist fact, that the mean of those latent variables inside the VAE engine, which we will see shortly, can determine the type and the actual number. So knowing only the mean of the latent variable, you can properly guess what that number is. So it's basically very easy to generate many digits just like by knowing this. So you can basically change the mean of those latent variables. If you have, let's say, two, Z0 and Z1, you can just change the means of those latent variables, and you can come up with many numbers which are similar to the 9s you have in your data set, but they're not really there. So you can basically do data augmentation very easily in the case of MNIST. So what is the actual application that we're going to see? We're going to see how a distribution and the shape of the distribution can be reproduced using a VAE. And for that, eventually, what we're going to calculate eventually from that distribution is a risk measure called value at risk, but you can use any other risk measure or any accuracy or performance measure like Sharpe ratio, because as soon as you have the distribution, as soon as you have all the scenarios, then you can use it to easily produce many samples. You probably have seen value at risk. It's basically telling you that the loss beyond that actual number that we call VAR, which could come actually in dollar values or return percentages, has a confidence, let's say probability of alpha, for example. Let's take a look at the architecture of a variational autoencoder. On the left side, we have a portion that is the input of the VAE, that is the actual real scenarios that has happened in the market. These are stock returns, but we need to actually standardize them to make sure that they're between 0 or 1, or between -1 and 1, depending on the actual preference for that you have for your network. I'm going to assume that X represents a sample from actual market data, and Z in the middle is the latent variable. So that is the variable that needs to change to give me, after the network is trained, that is the variable that needs to change to give me new scenarios on the right-hand side, which is a decoder. Now, the good thing is that when you're actually simulating from a distribution that you don't know what type of distribution it is, normally we know that distributions of return in the market are not normal. They have fat tail, they have very strange behaviors, and they are ambiguous, meaning that the distribution changes from time to time. And therefore, sometimes you need to change your parameters if you're using a parametric model. What I need to actually mention is that we're not really using a parametric model. And one of the advantages of this model is that in the middle, if you are simulating from the latent space, you're simulating from normal distributions. Now, because the normal distribution has a mean and a standard deviation, one might actually claim that this is a parametric model for the distribution of the return, but it's really not the case. Because the distribution of the simulated returns depends on a lot of other weights from the left side, the encoder, and the right side, the decoder. And those parameters are actually fitted to the model. And as we can see, eventually, the means can be set to 0, and the standard deviations can be set to 1 for the latent space variables. With regards to the probabilistic functions involved, the VAE consists of a probabilistic encoder model, which we denote by Q of phi, and a probabilistic decoder model that comes after on the right side of the diagram, and we show that by P theta. And for generating new data, first a value of the latent variable for each number of latent variables that we have. Here we have Q latent variables is drawn from the prior distribution, which is normal of 0 and 1, and then Xi is generated using the weights that we have for the decoder part of the network. I don't want to talk about the details of the learning process for this network, but I can just point out that we use the KL divergence for the loss function that is based on the KL divergence. Doesn't have a closed form solution, but there's a lower bound which is given as a sum of some of the parameters, including the mean and standard deviation of the latent variables, which need to be actually calculated. And it is not difficult to actually minimize that lower bound. So I don't want to talk about the details, but you can check them in the paper that we have. But eventually what we do is that we use a set of rolling windows with training set, validation set, and a test set, where the simulation is basically happening in the test set, and the simulated returns in the test set is used to calculate the return of the portfolio for that specific period. One thing I need to emphasize is that deep learning models normally require standardized inputs to improve the numerical stability of their model, and to basically somehow reduce the training time. We standardize each daily return according to the rolling mean and standard deviation, or alternatively, we can use exponentially weighted moving average of the mean and standard deviation. It probably won't make a difference as much. And within each rolling window, these standardization is going to happen before we train the model, because we know that the inputs of the network need to be numbers between 0 and 1. Therefore, this is necessary to use some kind of a transformation to standardize the inputs before feeding them into the network. So having the model set up, we have a loss function like this. The first part in the right-hand side of the loss function equation is going to assure that the simulated numbers and the distribution of pairwise returns from the left-hand side and the right-hand side are as close to each other as possible. And the second part with the coefficient beta is going to make sure that your latent space is indeed following a normal distribution. So if you want to have a better input data reconstruction, you can make beta as small as possible. And when the beta is larger, it's going to put more weight on the second term, making sure that the distribution of the latent space is normal. So it's basically a trade-off. If you've seen generative adversarial networks where you have a generator and a discriminator, you normally have to make good trade-offs to have like good results. And another thing is that we're using stochastic gradient descent algorithm to basically minimize this loss function. Now, when it comes to the actual simulation engine, we are generating samples from the latent space like zeta, and then based on those simulations, we're using the decoder function to create many samples, as much as we would like to have. As I mentioned, one of the advantages of this approach is that the VAE engine is somehow creating the shape of the distribution, meaning that when you're standardizing the returns and you're feeding them into the model, eventually on the other side, on the decoder side, you need to de-standardize to have things which are in terms of returns, for example, because if you're standardizing the returns, feeding them into the model, then on the other side, you're going to have objects which are similar to your inputs, and your inputs are standardized. Therefore, you need to do some kind of a reverse, like inverse Fourier transformation, for example, to get what you really want. And in that process, one thing that is quite interesting is that in that process, you can use your preferred model for predicting the mean and standard deviation of the model. Let's say ARMA and GART or whatever that you might want to have. And then you can do the de-standardization. So this engine is only creating the shape and something that isn't explained by the mean and standard deviation. And we know that there are so many methods for predicting the mean and standard deviation of a model. And that is something that we don't really have a lot of problem doing. It's usually the case that the shape of the moments beyond the second moment, including the skewness, the kurtosis, is going to give you a lot of errors and a lot of problem in terms of calculating whatever that you want to calculate, including like risk measures or performance measures and so on and so forth. So this equation is actually it's one of the advantages of the model, that you're only reproducing and simulating things which are normal distribution, and then you can have your own predictions of the standard deviation and the mean. So the VAE engine is basically, to make the long story short, is doing the hard work, and the easy part, not that it's the easy part, at least for risk calculations, the easier part is using a well established model like GARCH or eGARCH or Caviar or something like that to basically predict the standard deviation. And as soon as you have your predicted values, you can just put them into this equation, and from what you have produced from the VAE engine, you can have many different scenarios. And these scenarios, they have similar shapes to the actual input that you have used for training your model. Now we can use the generated scaled returns to calculate the return of the portfolio using the actual weights. We use just 1 over n as the weighting scale for the portfolio, but it could be changed easily. And we can observe that in the training data, VAE could be tuned very effectively. Indeed, we have used a hyperparameter tuning engine called Optuna, which is quite effective, and we were extremely happy with its performance to make sure that the hyperparameters of the model are also tuned as properly as possible. Now, if we could actually increase the dimension of the latent space, which in our case was 10, we could probably get a better fit, but it comes with computational expense. Let's take a look at the impact of the regularization parameter beta in how the return simulated by the engine is similar to the actual return in the market. When we actually change the beta, when the beta is very small, let's say it's equal to 0, then the second part of the loss function disappears, and then considering that the dimension of the latent space is rich enough and it's high enough, then the synthetic data and the real data, as you can see in the panel A, cannot be differentiated as much. But when we're increasing beta to a number, let's say half or 1, then we can see that these two distributions for the correlation histogram of the synthetic data and the real data, they actually change somehow. This data is coming from approximately 100 stocks in S&P 500. And of course, if you can actually decrease the dimension of the latent space, you would see in the panel C that the differentiation between the synthetic and real correlation histograms is even more visible. One of the advantages of the VAE engine for generating financial returns and financial samples is that it somehow, because you actually create more samples and you make averages among those real plus synthetic samples, is that the overall noise in your data set is going to be decreased due to the averaging effect. So you can basically calculate the signal to noise ratio in the real data set, and you can compare it with the signal to noise ratio on the entire sample of synthetic plus real samples. And then it's quite intuitive that in the second case, you're going to have a much higher signal to noise ratio. One way to actually measure this mathematically is the Marchenko-Pastor theorem, which states that the distribution of eigenvalues of a correlation matrix follows a distribution that is called, well, by the name of Marchenko and Pastor. So this Marchenko-Pastor density function, what it actually gives us is that in a range of lambda minus and lambda plus, where lambda minus and lambda plus are given eigenvalue numbers, and the interval is the support of the density function. The eigenvalues that are closer to 0 are associated to noise, and the ones that are far away from zero are more significant eigenvalues that can be associated. For example, the largest one can be associated to the market eigenvalue factor, and so on and so forth. So this distribution can give us a picture of how much any simulation engine, including the one that we are using with the VA engine, is reducing the amount of noise in the correlation matrix. So let's take a look. When we fit the correlation eigenvalues from the real data to the Marchenko-Pastor distribution, and then we use the synthetic data. So in the panel B, we're actually adding the synthetic data to the real data. So it's better to say that panel B is synthetic data plus real data correlation, the correlation generated from the combination of the two. Then we can obviously see that the fitted Marchenko-Pastor distribution in the second case has much lower noise, as the eigenvalues under the density function of the Marchenko-Pastor PDF, they can be associated to the noise present in the correlation matrix that is generated from the data. Now, when we use the VAE engine, the Variational Auto-Encoder, then we observe that the sigma squared is 63%, meaning that the rest, 37%, is attributed to signal, which is a fairly high improvement compared to 2 or 3% signal that is usually present in real data that is taken from the market. Now, another way to compare these two correlation matrices is to calculate the eigenvector overlap between them as a function of their rank. So if the rank of the correlation matrix is, let's say, n, we can look at the eigenvector overlap and how it changes over time. So one can simply look at the dot product of the eigenvectors of the two correlation matrices, and it can be seen that there's a fairly high overlap that is confirmed by a seminal paper by Ladoux from 2000 that explains how not only the eigenvalues are improved, but also the overlap between the eigenvectors is also significant for the first, let's say, 10 highest eigenvalues. So we showed that our model is doing a pretty good job in terms of improving the quality of the data when it comes to signal and noise. We have also used some, in our paper, we've used some measures of to compare the result of risk measures, for example, value at risk and expected shortfall, including the Cupic method and Christopherson method. Our results show that although the number of non-covered losses in the backtesting is consistent with the chosen confidence level, they're not independent of each other. And a fairly pleasing result from our paper show that only caviar gauge and EBT gauge, which are fairly complicated models, can outperform our model, and our model is able to basically do much better than the rest, except for these two fairly well-known and established methods. So to summarize, we've proposed a non-parametric, or you might want to call it semi-parametric approach that can use the least possible assumptions because it is basically using a neural network, and therefore it doesn't really make a lot of assumptions about the distribution of your return and so on and so forth. Our model can let you simulate from a very simple distribution, normal with mean 0 and standard deviation 1, and create fairly complex distributions. Of course, it needs to be taught. It needs to learn first before doing this, which is the hard part. The good news is that when you actually set up the model, when the model learns in the training set, then the ratio of signal to noise is increased quite significantly. And this Monte Carlo engine can be used for anything that is using simulation. So whatever, including like calculating risk measures or anything that provides a requires a Monte Carlo engine, can use the VAE-based model that we have proposed. The other advantage is that the risk manager can use any predictive model for their return and standard deviation. So it's kind of a modular setup. You can actually change your predictive model for the return and change your predictive model for the sigma squared, or any measure of the standard deviation. And then you can just plug it into the model. The model is only producing the shape of the distribution and lets you actually choose your own predictive model for the return and standard deviation. This part, the literature is very rich, but when it comes to creating the shape of the distribution, it's not. So it seems to be, we claim that the paper is a good addition from that perspective as well. And finally, unlike many other models, the encoded value at risk and this VAE-based model does not take into account any correlation matrix, which is a good thing, actually. It only takes in predictive mean and predictive standard deviation, and then the dependency and the shape of the resulting distribution for the return of the portfolio is basically regenerated by the engine. All right, that was my presentation, and I hope that you like it and you find it interesting. I thank you very much for your time and your attention.